Hello, students. We have finally made it to the last topic of Unit 0, which is what we're going to be discussing and going over in this video, and Topic 4 of these notes. Topic 4 is on something called a chi-square test. So in topic 3 in the last video, we talked about standard error of the mean, which is when we're using statistics to actually show if our data is statistically significant and meaningful enough to support a claim that we're trying to make. Now, a chi-square test is also a statistical test. It's different than standard error, and we use it for slightly different reasons for different situations. But a chi-square test is, again, we're going to be using statistics to see if our data is statistically significant or not in order to figure out what's going on when we look at our data. And so let's jump into it, and we'll do a couple examples, and hopefully this will make a lot of sense. So a chi-square test, which is often written as this Greek letter chi, it looks like a variable x, but it's like x squared, but that's the Greek letter chi. This is a test. It's also called a goodness of fit test, but this is a common form of statistical test used in biology. Like I said, this is the one of two types of statistics you guys need to know for this class. We already talked about standard error. This is the other one. And basically, we use a chi-square test in order to determine if the observed distribution of a given phenomenon is significantly different from an expected distribution. And so what that means is when we're looking at, let's say we're looking at a situation where there's a certain number of outcomes that are possible for that situation that we're testing. There's certain outcomes that can result from this thing we're testing. And we're going to go ahead and look at how many times each of those outcomes occur for this thing that we're testing. And we're going to look, and that's going to give us a distribution. We're going to see how many times outcome 1 happened, and how many times outcome 2 happened, and how many times outcome 3 happened. And we're going to look at that distribution, and we want to know when we get our results, is that distribution of outcomes, these different outcomes that we're getting, and the different number of outcomes that we're getting for each of these possibilities, is that matching what we were predicting was going to happen, or is it not matching? And we're going to use a chi-square test to help us figure out statistically if it in fact is matching or not matching what we thought would happen. And so if none of that made sense, I don't blame you. But like many things, it's a lot easier to understand if we look at an example. So let me give you a super easy example first, and then we'll do another easy example, but we'll go more in depth. So say I was like flipping a coin, and that's a super easy example. Like flipping a coin, there's two outcomes. You can either flip heads or tails. It's going to land on heads or it's going to land on tails. So there's two possible outcomes. And let's say that you, for a coin, a normal coin, we would expect that it should have a 50% chance of landing on heads or landing on tails, right? And so let's say I take a coin and I flip it. Let's say I flip it 100 times. Okay, and I'm going to track how many times it lands on heads and how many times it lands on tails, my two different outcomes. And I'm going to keep track of that and then look at the distribution of those outcomes once I do all 100 flips. And let's say at the end, my distribution is that 45 times it landed on tails and 55 times it landed on heads. And so the question becomes, does that data, is that consistent with the fact that we were expecting a 50-50 outcome? And so, first of all, I think you guys all would not be surprised to know that if in fact you had a coin that did truly have a 50% chance of landing on heads or tails, that it's no surprise if it doesn't exactly land on tails or heads 1/2 of the time. And so, like I said, if it landed 45 times on tails and 55 times on heads, that shouldn't make anyone probably super suspicious or in disbelief that the coin had a 50-50 shot at landing on heads or tails, because there's something called random chance, which is always going to have an effect on our data, where by random chance alone, or if you want to call it coincidence, certain things might happen more often than they're supposed to, or less often than they're supposed to. And it's not because of anything weird going on or anything going against what was supposed to happen. It's just just by random chance alone, that's what's going to happen sometimes. But the question becomes, when would the data look so weird or weird enough to convince you otherwise that maybe the coin didn't have a 50-50 chance? What if it was 40 times it landed on heads or tails and 60 times on heads, or 30 and 70, or 95 and only 5 times on heads? And so obviously all of those are possible in the universe. If you had a fair coin, technically there is a possibility of it landing all 100 times on heads, even though it's a 50-50 shot. But in science, there's going to come a point where something is so improbable, so unlikely, that really the better explanation is that something else is going on. And we can use a chi-square test to figure out when that's happening, when the outcome we're getting is so weird that it actually is suggesting that what happened was not what we were expecting to happen, that something else is going on. That's when we use a chi-square test. So maybe that makes a little bit more sense now, but we're going to go through an example with kind of like a coin, but let's do a dice because it's more fun. Because for a dice, a 6-sided dice, there's 6 possible outcomes. And so we're going to walk through this example together in this video, and I'm going to show you guys how you would use a chi-square test to figure out what's going on with this dice. So let's say I'm suspicious that a 6-sided die is loaded and it does not have an equal chance of landing on each side. So my friend, he's doing some sketchy things with this dice. I don't know, but I'm starting to get really suspicious. Like it really seems to me like this dice does not have an equal chance of landing on each side, 1 through 6. And so let's say I take this dice and I test it, and I'm going to roll it 60 times. And after I roll it 60 times, here are my results. Okay, here's what I observed happen when I rolled it 60 times. Here's how many times it landed on a 1, a 2, a 3, a 4, a 5, and 6. And you can see it hardly ever landed on a 3, and very often landed on a 6, and very little often landed also on a 5, it looks like. And so when you look at this data, the big question becomes, okay, would this data support that the dice had an equal chance of landing on each side? Because obviously it's not going to land perfectly the same number on each side. There's random chance, right? But when does it differ so much from what we expected to happen that it's now strong enough data to support something else, to maybe support the claim that this dice doesn't have an equal chance of landing on each side? And so you might look at this data and think it's super suspicious, or you might look at this data and you're like, well, that seems super possible for a normal die. And so this is a perfect situation where we use a chi-square test to figure out how weird is this, okay? And so here's how you do a chi-square test. There's different steps. Step 1 is you need to first and foremost figure out what's called the null hypothesis and an alternative hypothesis. And so we've talked about hypotheses before. In a lot of experiments, you can come up with something called a null hypothesis. A null hypothesis is basically you stating, or for your hypothesis, you're going to state that the data that you're going to get from your experiment is going to be consistent with a specific expected distribution. So the data you're about to get, you're going to predict for your null hypothesis, you're going to predict that data is going to match some very already determined expected outcome. And usually that outcome is going to be the result from random chance. So you're basically just going to say that what's going to happen in this situation is this outcome, which would happen due to just random chance. By random chance, it should be like it should land on each side the same amount of times. And usually in the null hypothesis, we specify the proportion to be found in each category. So to make that make sense, maybe for the dice example, the null hypothesis should just be that the dice, you should just by default for your null hypothesis claim that the dice should be rolled 1/6 of the total, that each number on the dice should be rolled 1/6 of the time, right? You could just say that as your null hypothesis, but that's your null hypothesis. It's just if everything was up to just random chance, what should the outcome be? What should the distribution look like? And for a dice with 6 sides, if it's a fair dice, our null hypothesis is going to be, well, it's by default, like it should just land on each number 1/6 of the time. right? That's your null hypothesis. Now you might think otherwise. You might think, actually, I don't think that's not my hypothesis. I think that it has a higher chance of landing on a certain number. Well, don't ever say that for your null hypothesis. For your null hypothesis, think dull hypothesis. Null hypothesis is the dull hypothesis. It's like just the most boring prediction. Like if everything was happening the way it was supposed to happen and nothing weird was going on, that's your null hypothesis, okay? Now there is something called an alternative hypothesis. The alternative hypothesis, that's when you would now predict basically the opposite of the null hypothesis. You're gonna predict now that there is something gonna happen that's gonna make it not match the expected outcome. And so from the dice example, I could just easily say for my alternative hypothesis, I would say one number is favored on the dice and will be rolled more often than the other numbers. That would be a good alternative hypothesis for this dice rolling experiment. Or you could just make it the opposite of the null hypothesis. If the null hypothesis says that each number on the dice will be rolled 1/6 of the time, you can say for your alternative hypothesis, you could say each number on the die will not be rolled 1/6 of the time. That would be fine too, which is basically saying the same thing here. Or you could pick a number. You can say 6 is going to be rolled more often than the other numbers. But for your null hypothesis, this is what's really important. Your null hypothesis, which is the really important one here, moving forward in the next steps, that has to be the one that's just the by default normal outcome. That's usually just by random chance what should happen, okay? And so moving on to step 2, using that null hypothesis then, you're going to figure out what are the expected counts for each outcome that was possible. And so that's consistent with the null hypothesis. So for this dice, if your null hypothesis was that each number would be rolled 1/6 of the time, well then if you rolled the dice 60 times, you need to now go ahead and write down, okay, well, what according to your null hypothesis, the null hypothesis, what were you expecting to get? And if your null hypothesis was true, and if your data perfectly match your null hypothesis, then it should be, if you did roll the dice 60 times, it should be 10, 10, 10, 10, 10, and 10, right? That's consistent with our null hypothesis. And so those are your expected outcomes. Like that's what you were expecting to happen. Now, did that happen? No. Is that surprising that it didn't happen? It's not surprising. But what we're about to see is we're about to test if what actually happened is statistically significantly different than what we were expecting to happen. I'll show you that in a second. But for now, we need to at least come up with our expected numbers. Our expected numbers should have been 10, 10, 10, 10, 10 for this situation with the dice being rolled 60 times. And here's what actually happened: 15, 10, 4, 10, 2, 19. Hopefully you're all with me right now. You might be thinking about the alternative hypothesis. Don't worry about that. Really, that one doesn't really matter. Okay, what we want to do now is take that null hypothesis and we're about to test to see if it's correct by coming up with these expected numbers, which is why for your null hypothesis, don't choose something interesting or weird. Like for your null hypothesis, don't say that one of the numbers is going to be rolled more often than another number, because then you need to come up with these expected numbers, and these expected numbers need to match the null hypothesis. And if you're saying a certain number is going to be rolled more often, well, then what are you going to put for these expected numbers? At that point, you're just making up things. You're going to say like 20, 5, 10, I don't know. You're going to just make up numbers, which is not what we want to do. We want to come up with some very solid prediction, okay? So here we go. That's our expected numbers. Now, step 3, this is where it gets fun. You are now going to compare the expected counts and the observed counts using the chi-squared formula. And this is going to provide us the chi-squared value. So there is a formula for chi-squared to calculate what's called a chi-squared value. This is provided to you on your formula sheet. You don't have to memorize this. But unlike standard error, this formula you do have to use. So you guys will be expected to be able to use this formula and calculate chi-squared values from this formula. And this formula might look scary at first. It's super easy. I'm going to show you. I'm going to do it with you right now in a moment and show you how to use this formula for the data that we're looking at with the dice. But it says chi-squared equals, and by the way, this is chi-squared. This is just the symbol for chi-squared. This is not x squared. So I'll just warn you right now, and I'll warn you again in the future, do not square root anything at the end. So some students look at this and they think they have to take the square root to solve for x. You're not solving for x. This is just the symbol for chi-squared. So you're gonna look at this side of the equation. So chi-squared, this value is going to equal, and this is sigma, which means the sum. And what you're gonna do is you're gonna take the observed value and you're gonna minus the expected value. You're going to subtract those and then square it, and then you're going to divide by the expected value. But you're then going to repeat that for all possible outcomes, which again, this will make sense in 1 second. And then you're going to add it all together, and you're going to end up with a certain value. So down here, I kind of typed it out. It doesn't, I don't know if you can follow this all typed out, but I'm going to show you on my camera because I think that would be easier. So let me pull that up here. So here's the formula for chi-squared. Again, you don't have to memorize it, but you do have to use it. So chi-squared equals this. And so here's from my dice experiment. We were expecting, again, to have 10, 10, 10, 10, 10, and 10. And your guys' notes actually on the left side, these are some of the questions you have to answer. So hopefully if you have your notes out, you can fill this in. There's a table for you to fill in. And then it wants you to show how to show your work on how you figured out the chi-squared value for this dice example. And so here's what we're going to do. I'll show you what this looks like. So chi-squared equals, so we're going to plug in these numbers now. I'm going to show you how to plug in these numbers to this formula. Look at outcome number 1. So there's 6 different outcomes here. You can roll a 1, 2, 3, 4, 5, 6. Let's say rolling a 1. Rolling a 1 was one of the outcomes. Now, how many times did we observe a 1 being rolled? 15. So I'm going to plug that in. So this is going to be 15 minus how many times was I expecting it to happen? I was expecting it to happen 10 times. You're going to minus those 2 and then square it and then divide it by the expected number, which again, I was expecting a 1 to be rolled 10 times. Now that was for one of the outcomes, but there's 5 more outcomes. So then you're going to look at the next outcome, rolling a 2, and you're going to do this again. Well, for rolling a 2, you observed that it happened 10 times and you were expecting it to happen 10 times. So you're going to do 10 minus 10, and you're going to square it, observed minus expected, squared, and then divide by the expected number, which for a 2 was also, you're expecting 10. And then you're going to add that to the other outcome. That's what the sigma means. You're going to add this all together for each possible outcome. So I'm going to go ahead and repeat this 4 more times, and we're going to add it all together in the end. So let me go ahead and show you what it looks like plugged in, which is going to look scary, but you'll see it's not that bad. And you guys get to use calculators in this class and on the AP test, which makes it way easier, but there's still room for you to mess up, so be careful. But for rolling a 3, you observed it happened 4 times, but you were expecting it to happen 10 times. You minus it, you square it, you divide by the expected, which is 10. I'm going to do that for the next one. Rolling a 4, you observed a 4 being rolled 10 times. You were expecting it to happen 10 times. You subtract it, you square it, you divide by the expected, which was 10. For rolling a 5, you observed that it happened twice. You were expecting it to happen 10 times. You square it, you divide by 10. And then lastly, for rolling a 6, you observed it happened 19 times. You were expecting it to happen 10 times. You square it and you divide by 10. You guys with me? That's what this formula looks like with all the numbers plugged in for this situation. Since there's 6 possible outcomes, I had to do it 6 times and then I add it all together. In a lot of situations, there's way less than 6 outcomes. Like if I was doing heads versus tails, for flipping a coin, there's only 2 outcomes. So you'd only do this twice, 1 for heads, 1 for tails, and then add it, which would be way easier. But we're going to go ahead and work this out. From this point on, I'm heavily relying on your guys' math skills. Now that you're in an AP class in high school, I trust that we can all get to the same answer, especially if we're using calculators. I don't really care what you do at this point. Except don't mess up. So like come up with the right answer, okay? Don't do something weird, okay? So if you want to just follow how I do it, I'm just going to show my work and do it the way that makes the most sense to me. And I don't have a calculator in front of me, but I think I can do this without a calculator. So for example, let's start simplifying. 15 minus 10, that's negative 5. Sorry, that's 5. I already messed up. 15 minus 10, that's 5. 5 squared is 25 over 10. So I'm just going to simplify this. That's 25 over 10. Right? So that becomes this. This next one is 10 minus 10, which is 0. 0 squared is 0. 0 divided by 10 is 0. So I don't even know. I'll just put 0 over 10 for now, just to show you it's simplified, right? And then 4 minus 10, that's negative 6. Negative 6 squared is positive 36 over 10. And then this next one is 10 minus 10 again, that's 0. Squared is still 0 over 10. And then 2 minus 10, that's negative 8. Negative 8 squared is positive 64 over 10. And then 19 minus 10, that's 9. 9 squared is 81. 81 over 10 is, well, let's just leave it like that. So there, I'm just trying to do this in baby steps for you guys. I just took each of these fractions and I simplified. And so from here, I'm just going to, well, since they all have a common denominator, I'm just going to add it all up and divide it by 10. Or you can do each of these divided by 10 and add it up. At this point, hopefully we're really close, but I'm just going to quickly, let's see, that's going to be 36 plus 64, that's 100. And then we have 181, and then 181 plus 25, that's going to be 201, 206. 206 over 10. I add all the numerators since they have a common denominator. Anyway, you do 206 divided by 10. My final answer is 20.6. This is my chi-squared value. And that's hopefully the answer that all of us are getting, 20.6. That's the chi-squared value. Okay, that's the answer here to this formula, 20.6. Again, you can do this however you want, as long as you plug it in and you get this answer. So the answer you should get, 20.6. Now, what does that mean? You have no idea yet, but that's your chi-squared value. So you can copy that in your notes on the left side for one of those questions, but I'm going to go back to this. So, and that's what I got down here, 20.6. That's your chi-squared value. Now, the next step is you're going to use what's called a chi-squared table to compare your calculated chi-squared value with the critical values that correspond to the correct degrees of freedom. So there's something called a chi-squared table. This is provided to you on your formula sheet, so you don't need to memorize this. On this table, it's showing you a couple different things. First of all, it's showing you different 8 degrees of freedom. And so for every experiment or example that we're doing chi-squared with, there's going to be a certain degrees of freedom that applies to that situation. So for rolling a dice, there's a certain degrees of freedom that applies to that scenario. And to figure out degrees of freedom, it says right here, degrees of freedom equal the number of possible categories minus 1. So for a dice, this dice example, there's 6 possible outcomes, right? You could roll a 1, 2, 3, 4, 5, 6. 6 possible outcomes minus 1. That means the degrees of freedom is 5. So you're always going to minus 1 from the number of possible outcomes. So the degrees of freedom is 5 for this example. So on this table, the only thing that matters is right here. So ignore the rest of the table. Everyone just look at 5 degrees of freedom right here. Okay. Now the next thing you're going to look at is you're going to see 2 numbers here. These are called critical values. You need to figure out the correct critical value to look at. And I'll show you what that's going to do for you in a second. Now, each of those 2 critical values correspond to different p-values. These p-values, there's basically, usually the question will tell you what p-value to use. By default, you can just use p-value of 0.05. So if no one's telling you which one to use, just use a p-value 0.05. You don't have to look at 0.01. Basically what this means in a second is if you're using this p-value of 0.05, if you're looking at this top number, in the end, that's going to give you 95% certainty if you're using a p-value of 0.05. It's going to give you 95% certainty that your data is what you think it is. And then if you use a p-value of 0.01, that's going to give you 99% confidence in your conclusion here in a moment. You'll see what I mean in a second. But like I said in the last video, we always just default to 95% confidence. That's all we need. And so usually you're just going to almost always use a p-value of 0.05. I've actually never really seen a situation where anyone asks you to use a p-value of 0.01. So you can just look at this first number, 11.07. So 11.07, that's going to be the critical value. that we're looking for. Okay, 11.07, that's our critical value. Now our chi-squared value, we already calculated that, that's 20.6. So this is the chi-squared value. This is the critical value, 11.07. You guys with me? Okay, two different things. So then we move on to the last thing here. So here's what you're going to do. You're going to figure out if your null hypothesis is accepted or rejected. So in the end, we're either going to accept our null hypothesis. We're going to say our data is consistent with the null hypothesis. So we're going to accept it to be true because we don't have data to go against it. Or we're going to reject our null hypothesis. We're going to say that our data actually goes against what our null hypothesis was saying. So we're going to go ahead and claim that our data is strong enough to say our null hypothesis is probably wrong. Okay. Now to figure that out, to figure out if your null hypothesis is accepted or rejected, you're going to see if your chi-squared value exceeds the critical value. Again, for a p-value of 0.05, which you can just look at that one that I showed you earlier. If that's true, if your chi-squared value is larger than the critical value for a p-value of 0.05, that means you can reject the null hypothesis. Okay. And what that means, it means that the difference between what you observed and the expected outcome, the outcome you were expecting, the difference is statistically significant, and you're 95% sure that there is actually a real difference between what actually happened versus what you were expecting to happen. And there's only a 5% chance that the difference was because of random chance or variation. So to kind of illustrate that, if you look at our chi-squared value, it was 20.6, which is larger. It exceeds the critical value of 11.07. Therefore, because the chi-squared value is larger than the critical value, we're going to say that the null hypothesis is rejected. We're going to reject it. We're going to say that the null hypothesis, which again, remember, our null hypothesis was that each number should be rolled 1/6 of the time, which gave us these expected numbers. What we're saying now is after doing this chi-squared test, we figured out that this observed outcome, we're saying now that it's statistically significantly different than what we were expecting to happen. This expected outcome is not consistent with what was actually happening, which means that our null hypothesis, it wasn't a good hypothesis. It didn't accurately predict what was going on. It's saying that the difference between all these numbers is not due to random chance probably. It's very unlikely. There's only a 5% chance that these numbers are consistent with these numbers, and it's just because of random chance that they're different. There's a 95% chance that this is just the incorrect expectation from this dice. There's a 95% chance that our null hypothesis was just wrong, that this expectation was incorrect, that our dice is behaving in a way that is statistically significantly different than what we were expecting it, or how we were expecting it to behave. That's what this means. So that's what's going on in this situation. Now, if your chi-squared value was less than the critical value, for a p-value of 0.05, then you would accept the null hypothesis. And that means that the difference between what you observed and what you expected is not statistically significant. And any difference that you see is probably just because of random chance. So let's say that our chi-squared value was like 10. And so it wasn't 10, but let's pretend it was 10. Our chi-squared value is 10. 10 does not exceed 11.07. So then we would say, if that was the case, if the chi-squared value was less than 11.07, then we would say, okay, what actually happened is consistent with what we expected to happen. We would say that the null hypothesis, we're going to accept it. This data doesn't go against the null hypothesis. This data is not statistically significantly different than what was supposed to happen. And it's probably just because of random chance that the numbers were different. That's what we would conclude if our chi-squared value was not greater than the critical value. But since it was, we're going to go ahead and say, yeah, this data is sketchy. This data does not match what was supposed to happen according to the prediction that the dice should land on each number 1/6 of the time. And we can say that with 95% certainty. And in fact, if you look at this table for a p-value of 0.01, here's what that means. If you guys look here, our chi-squared value is also larger than that. Well, what that means is we can actually say with 99% certainty So not only are we 95% sure, but because it's greater than this critical value as well, we can say with over 99% certainty, this dice did not have a 1/6 chance of landing on each side. The null hypothesis is rejected. What actually happened was not consistent with what was expected to happen. And this is not due to random chance. There's only a 1% chance at that point that this was due to random chance. There's a 99% chance that something weird is going on with this dice, making it behave differently than how we expected it to behave. So that's what a chi-square test is, and that's how we use it. So from the dice example, here's my conclusion. I would say, so like on an AP test, on a test question, you guys, if I asked you, okay, write a conclusion or determine if the null hypothesis is accepted or rejected, and then I ask you to justify why you're saying it's accepted or rejected, so that the AP people or me as your teacher know that you're not just guessing. I would say, here's what I would say. I would say the chi-squared value exceeds the critical value for 5 degrees of freedom and a p-value 0.05. So I'm telling them exactly where I'm looking. So I'm proving to them, like, I know exactly where I'm supposed to be looking. I'm looking at this critical value, and the chi-squared value that I calculated is greater than that critical value. Thus, because of that, that's my justification. Because of that, I'm going to say the null hypothesis is rejected. At least one of the sides, I don't know which side, but not all the sides have a 1/6 chance of being rolled. That's my conclusion here, okay, because my null hypothesis is rejected. So you guys have some questions. On the left side, I kind of did the first 2 questions with you, and then there's a new scenario that you're going to think through. It's a lot simpler or easier because there's only 3 possible outcomes. But try to do this one on your own and come up with the chi-squared value, and then figure out the critical value by looking at the chi-squared table and figuring out the correct degrees of freedom. And then ultimately figure out, is your null hypothesis accepted or rejected, and justify your answer, just like I did in the notes for the dice example. So good luck with that. If you guys have questions, obviously write them down and ask me in class, but that is it for this video. Thank you guys.